Right. So computers and text. How do computers go about storing text inside the computer and processing text? Spend some time on that today. So here's a secret message. Series of 2-digit, are they in base 10? Base 2 or base 16? What do you think? Yeah, what gives it away as being base 16? Anybody know? Yeah. Yeah, there's letters where there should be numbers. So if you see letters like that, if you see a G, then it's certainly not base 16. But if you have letters between A and F, along mixed in with other numerals, that's probably in hexadecimal. Now, when you're representing text, the original way of doing this was when the computers first came out, they used a 7-bit standardized code called ASCII, and it had 128 different characters in it. So you think about that, is that enough characters to support the English language? Yeah, you'd think so, because you have, what, 26 lowercase letters, 26 uppercase letters, you got some numerals there, you got punctuation. Was that enough to cover most of those? I'd say yeah. But then, not everybody speaks English, right? When you open up for other languages, it's a little bit, it's completely inadequate. So what does ASCII stand for? American Standard Code for Information Interchange. It would be really kind of dumb for computers not to be able to talk to each other. An IBM computer wouldn't be able to talk to a PC. PC couldn't talk to a Linux box because they'd have different encodings for how they send letters around. And this was the case when I was just starting my career. IBM was using this code page called ASCII, and we'd constantly have to translate between that coding system to ASCII, depending on where we were going in the system. A lot of extra processing that didn't really need to happen. What the American companies did is they kind of got together and they agreed upon, okay, when you have this hexadecimal number 2C, that's going to represent the letter A or the letter C or something like that. They came to agreement on that. So here's the lowercase letter on the ASCII code chart. You can see when you type a letter into a word processor, type in the letter A, let's say, what gets stored in the file is this binary pattern. If you translate that into decimal, that's 97. If you translate that number into hexadecimal, it's 61. Notice I didn't say 61, it's actually 61. But the table is much larger than this. This is just a portion of the table. So if we take the time to go and translate this, we look at 77 in the hex column, look across the table, and we see that's a W. And if you do that with the other hexadecimal numbers here, you'd be able to see the word welcome perhaps in the code. If you look in the file itself, the zeros and ones directly, I mean, this is what you see, just a bunch of zeros and ones. Okay? That's what it would look like. But it depends on the context. If the computer knows that, hey, this is a text file, it knows to take those binary numbers and translate them 8 bits at a time using this lookup table to figure out what letter that is. Say you type in the letter Z. A lot of people think on your word processor, it puts a little picture of the letter Z in your document. And then you type the letter E, and it puts a little picture of the letter E in your document. And the answer is that's not how it does it when you store a document. When you put in a Z, it puts in 01111010 for the letter Z. That's what gets actually put in the file. And then E would be, looking at the chart, 01100101. From a human standpoint, that would be really difficult to recognize. So what happens is you're in the word processor, you type this in, it stores these binary numbers, which are codes for translating these binary numbers into actual text. Now, somewhere in the computer, there's an array that has all the pictures of the letters in it. When you type in the letter Z, it uses the binary number code and looks up what the picture looks like in that table and then puts that picture on your screen. Just because you see it on the screen doesn't mean that's what gets stored. What gets stored is the code. The picture is separate in a separate table, and it's just used to show that value to you as a. So eventually everything on a computer boils down to binary numbers. Here's 2 text strings. What I'd like you to do is use your table and see if you can figure out what these two pieces of text are trying to say. Where's this table? Well, if you go out to the calendar for the class, and you go on day 3, you'll see an ASCII table right here. So just click on that, and then you can use that complete ASCII table to translate between the hex and the text. See, there's the whole table. I always find the first part of the table kind of interesting because they're not actually letters. They're commands to a teletype. Before they had computer screens, they had these things called teletypes. And you type something on this piece of paper, and it would go to the mainframe and then come back, and it would type the response. So you didn't have a screen, you had a piece of paper that kind of scrolled through this printer-like thing. So I'll let you do that. I want to make this distinction between the number 5 and the symbol 5. They have two different values. If you look inside the ASCII table, you'll see that for the symbol or the character 5, it has an ASCII value of 35, where the number 5 is just 5 in binary, I guess. And so what I'm asking here is, how can I take the symbol 5 and turn it into the number 5? What kind of math operation would you need to do that? Remember, these numbers here are in hexadecimal. You have to keep that in mind when you're working with this problem. All right, so here's an example. We take the symbol 5, which is 35 in hexadecimal, and we subtract off the ASCII value for the symbol 0. And you'll note that when we subtract that off, we can convert then that text space character 5 into the actual number 5. And we can apply this to other digits as well. If you take a look at 39 here, and we subtract off 30, I guess that's not 39, it's 39. So we look at the second column. You can use this for other numbers as well. Here's the ASCII value for the symbol 9. And again, we just subtract off 30, which is the ASCII value for 0, and we can convert then the symbol 9 into the number 9. You can also go the other way. Say you have the number 5 and you want to turn it into the symbol 5 or text space 5. You can just add 30 to the binary number and you can get its equivalent ASCII code. Okay, here's the next problem. Take a look at. So say you have the ASCII codes for the word dog, all in capital letters, and you want to replace it with the ASCII code for lowercase dog. In fact, you want to transform the uppercase dog into lowercase dog. Let's go back then to my worksheet. For the capital D, the ASCII value for capital D is 44. It's in hexadecimal. And you'll find that if you add 20 in hex to uppercase letter, it will give you the lowercase letter. 44 in hex is capital D. We add 20. 44 plus 20 is equal to 64, and that magically transforms that capital D into lowercase d. And this works for all the other letters as well. Here we have the capital letter O. Its ASCII code is 4F. We add hexadecimal 20 to it, and we get 6F, which is the lowercase form of O. So I was mentioning this earlier. So what happens when you type the letter A? Some think that the computer stores a little picture. In reality, the computer stores the ASCII code that represents the letter A in your document. So it's just a series of ones and zeros. Now, when you need to see it or when you need to print it out, it takes that code and it translates it into a picture to show on your screen or a shape to print on your printer. But internally, even the letters are binary numbers, but they're a binary code. Now, there's other coding systems out there. I used to spend a lot of time converting between ASCII, ANSI, and Unicode. I was an international programmer, so my job was to take English language programs for English language audiences and translate all the screens so that it would be in Japanese or Arabic or Spanish. And the problem with those languages on a computer is that the ASCII code page is only 7 bits wide. So how do you store, like Chinese How many characters are in the Chinese character set? Yeah, 7,000. I couldn't come up with a unique code for every single one. So what I used is something called Unicode. Let's first talk about ANSI. ANSI added one more bit to the encoding. So now instead of 7 bits, you have 8 bits. And that allowed for 128 more characters to be represented by that code page. So in ANSI, the ASCII page and the ANSI page line up directly, but say you wanted to put in some more international symbols, like in Romance languages, they have a lot of accented letters. You have kind of, like in Spanish, you have an upside down question mark. Okay, that's not typical in English. So those European languages are included in that second half of the code page. Different letters and symbols, a little bit bigger so that you can handle maybe European languages. But yeah, what about the other languages out there? You have Japanese, has 3 different code sets. You can do katakana, hiragana, and romanji, which they don't use very much. 3 different ways to write the same thing. Chinese, very difficult. Arabic, I had to do a system in Arabic over in Saudi Arabia, and that was challenging because in Arabic, the letters go from right to left instead of left to right. The numbers go from left to right. Very difficult. And each letter has 3, or actually could have 4 different shapes because it's a cursive type language. That was a real challenge for me to get a computer to be able to handle that. But I was able to do that, and we sold millions of dollars of computer hardware to Saudi Arabia because we were able to do the translation. So you can make a lot of money if you know how to do this properly. So what is Unicode? Well, it has every character of any language ever spoken or written on the planet Earth. That's a big code page. So it covers English, it covers Egyptian hieroglyphics, Sumerian writing, historical languages that aren't even alive anymore. All of these languages are represented in this Unicode page. So there's over 100,000 different symbols, covers 93 forms of human writing. What's neat about Unicode is you can write in multiple languages in the same document at the same time. You used to never be able to do that. So if you're a Spanish teacher, you could switch back and forth between English and Spanish and not have to do terrible translations. Of course, the internet now, which code page do you think they use now for the internet? Yeah, if you go to Google Translate or just browse around the internet, there's Russian out there, there's all these languages. The question is, well, what code page does the internet use? And the answer is Unicode. So I like Unicode. It makes my job as a programmer a lot easier, especially when I have to translate between systems. So there's a worksheet out online, and this is what I'd like you to do with this worksheet. I'm kind of getting tired of paper in my classroom, so I'm trying to reduce the number of things I have to dig through paper-wise. If you look at my office, I'm buried in paper. So we're going to do this electronically. So how do we do that? If you go to the calendar entry, you'll see the ASCII translation worksheet. So you grab that. Problem is you can't edit this. I can because I authored it. But right now I'm in view-only mode. So if I try typing, it doesn't do anything. The question is then, how do I fill this out? Well, what I would do is I would go to the File menu, and I would say Download as Microsoft Excel. And that'll put it down here. And then what I would do, now that you have it downloaded, I'd like you to do this, say Show in Folder. And I want you to copy that and put it in your H drive. For me, my H drive is actually my Z drive. So I'm going to plop it in here. Now that I got it in my H drive, oh, by the way, everyone has an H drive now. Is there anyone who doesn't have an H drive? I put all the names in last night. So I think everybody's covered finally. That always is quite a challenge. Then open up Excel and then use the translation worksheet that's attached to that calendar entry. Turn this in. Please don't tell your neighbor what it is. The whole idea here is pretend you're like secret spies or something, and you're trying to decipher this encrypted cipher. Not a very good cipher language. So this is where you put in your translation, and then once you're done with this, how do I turn this in? Well, you have a link in your H drive. Let me just bring up a random H drive here. So now it's time to turn it in. I'll close it here. And in your folder, you might have you'll have a shortcut that says Computer Hardware to Grade. This is in your H drive where you should have your Excel document. Fill that out and then just drag it into this shortcut. And that takes you to a spot on the server where only you and I have access to it, not your neighbors. And you would put the translation worksheet in there. It looks like someone has already done that. So whoever this is, I don't know who that is, has already finished it. So that's how we turn in things electronically, right?